Welcome. This question says a guitar string is fixed at both ends, as guitar strings are. It is 2 meters long. A transverse wave has a speed of 5 meters per second on the string. Then it's saying what is the wavelength of the first harmonic, and then it's saying what is the frequency of the first harmonic. Okay, so the first thing I'm going to do is I'm going to visualize my guitar string, and I know that this is 2 meters from there to there. So that's my length, if you like. And then I suppose the next thing I should do is picture the guitar string vibrating. Well, there's one mode of oscillation. And just, for the sake of it, let's just imagine a second mode of oscillation. And that would be, you see, the rule is that there's got to be, if it's fixed at both ends, there's got to be a node at each end. And provided that I stick with that geometry, there's a whole family of allowed solutions. And these are the harmonics. So I'm drawing the family of harmonics here. This is the wave, the string bouncing backwards and forwards. In this case, there's a node at each end. In this case, there's a node at each end plus a node in the middle. In this case, there's a node at each end plus 2 nodes in the middle. And basically, these are the first harmonic. This is the first. This here, it turns out, is the second. Not because it's the second in the order, but because of the frequencies that it produces. And this is the third harmonic. So there's a family of 3, and it goes on, continuously from there. Okay, so we're interested in the first harmonic, so we're interested in this one here. And if I look, how much of a wave is this? Well, there's my equilibrium line. And a wave looks like this. That's one wavelength. So I can have half a wavelength. So I'm going to say my L, the length of this guy, in this case is equal to lambda over 2. In this case here, we're not going to continue with this, but in this case here, that looks to me like a whole wavelength. And in this case here, that looks to me like a wavelength and a half. But in this case, we're talking about the first harmonic, so we're interested in this example. So this gives me that my wavelength is equal to 2 times L, which equals 2 times 2. So my wavelength is equal to 4 meters. So there's my first answer. And then my second answer is, well, what's the frequency? And I know for waves, V equals F lambda. So that means that my frequency equals my velocity over my wavelength. And I'm told that this velocity, the energy travels backwards and forwards along the string at 5 meters per second. And I've just calculated that my wavelength is 4 meters long. So this must be 1.25 hertz, not meters per second, hertz. 1.25 hertz. And if I was asked for the second harmonic, I'd do that same analysis on this diagram. If I was doing the third harmonic, I'd do the same analysis on that diagram. There are equations. You can look at the book, and there are equations, and one equation says that the lambda of a given harmonic is equal to 2 times the length over the number of that harmonic. And there's another one that says the frequency of a given harmonic is equal to the velocity over the wavelength of that harmonic. And again, it comes down to this decision you've got to make of do you remember all these equations and kind of like ignore visualization, or do you just visualize? To do this problem, all I've got to do is be able to draw these diagrams, and they kind of flow logically. And then I can interrogate these diagrams. And because I understand the basic ideas of, well, how much of a wavelength is this, and V equals F lambda, I don't need, in my opinion, I don't need these other equations. And if I change the system slightly, the equations can change. So the choice is yours, but either way, be able to do the answers. And there we have it.